Mr. Putnam here, and today I want to introduce you to the four fundamental forces of physics. We've talked about force and we've defined it as a push or a pull. Well, that's true, but you might say to yourself, well, there are hundreds or even thousands of ways that I can push or pull something. For example, the wind or my breath can move an object or a piece of paper. I can pressurize something like a fluid like WD-40 and move it that way. I can use electricity to power a drill and turn a screw. I can use magnetic force to change the direction of a compass needle. I can even use my muscles to take an object and throw it. Sorry about that sound. But even that sound wave is a pressure wave, which pressurizes the air and pushes it, compresses it, and when it reaches my ear, I hear it as a sound. And you might think that these are all different forces. Well, these aren't. These come down to four fundamental forces. In fact, most of them are only involved in one or two forces. So we're going to talk about what these four forces are that govern the universe. The first force is gravitation. Gravitation holds everything in the universe together. In fact, every object in the universe, every atom in the universe feels a gravitational attraction, however slight it might be, for every other atom in the universe. It's a universal force, which means that you and I, no matter where we are right now, are somewhat gravitationally attracted to each other. Very strange to think about. Even distant stars, you don't think they have any effect on you, but somehow they feel you and you feel them gravitationally. Kind of a trip. But gravitation is only a force that attracts things. There's also electromagnetism. And in fact, that's what keeps things from being attracted too much. For example, a star, as an intense gravity of our sun perhaps, is pulling all the hydrogen and helium together. The hydrogen and helium atoms themselves have electrostatic repulsion because, as you recall, the electrons in the outsides of those atoms are going to be repulsed by the electrons in the other atoms, which is the reason why, as we talked about before, you can't actually touch anything. Or when you sit down on a chair, you're actually hovering over the chair because the electrons in your butt are repulsed by the electrons in the chair. And you might deform the chair, you might push down on it, but all that's happening is you are reaching a position where you're going to balance that electrostatic repulsion with the force of gravity that's pulling you down. You're not ever going to touch another atom. Well, that's the repulsive form of electrostatic force, but there's also an attractive form. As you recall, if like charges repel, well, unlike charges attract. So the protons, for example, keep the electrons in orbit around the nucleus because the protons are positively charged and the electrons are negatively charged. So there's going to be an attraction that's going to hold the electrons close to the atom. And in fact, that electrostatic force is important also for electron bonding and things like that. But there are two other forces that are critical, even though we don't experience them on a day-to-day basis. Those two other forces are the strong nuclear force, which basically is what holds the nucleus of atoms together, which keeps the protons, which are all positively charged, from flying away from each other. There's an even stronger force that acts only over a very small distance. It doesn't feel like gravity or electromagnetism sort of universally. It only feels this very small distance within an atom and holds those protons together. And there's also the weak nuclear force, which governs radioactivity and allows a radioactive decay. Sometimes that means protons turning into neutrons or vice versa, which allows the buildup of nuclei in atoms. But those aren't forces that we deal with on an everyday basis. The interesting thing to think about, though, is that these forces have very specific values that are universal. Gravity always has the same value. If you have two objects anywhere in the universe, no matter what the objects are, if they have the same mass and are the same distance apart, they're going to have the same amount of attraction for each other based on gravity. And these forces are very important. It's very important that they're exactly what they are. For example, if gravitational force was any larger, stars would burn much brighter because there'd be much more force and energy pulling them together and causing sort of the nuclear reactions to take place. They'd be much more unstable. And if gravity was any weaker, things would be floating around much more, and there wouldn't have really been time for stars to, or actually not just time, but also enough energy to actually have them form heavier elements, which are required for life. There are similar sort of very tight parameters for the charge on these other, or I should say the values of these other forces, like the strong nuclear force, the weak nuclear force as well. And these values have to be fine-tuned in order for life as we know it, and really life in any form, to exist, which has caused some people to sort of posit the idea there must be a God, because someone has thought this through and has all these numbers carefully defined to actually make life possible. And other people have posited this other theory called the multiverse theory, which states that there may be, and we have no way of knowing this, millions, billions, trillions, gazillions of other universes, and we just happen to be in a bubble of a universe that has all the exact right parameters. So there might be millions of other ones that don't have those parameters and therefore can't support any type of life. Interesting thing to think about, and one of the interesting things that physics can kind of lead us to, philosophy, etc.